Hello, and thank you for joining this webinar. Today we'll review two technical standards that were revised through our state's technical standard development process. This process is managed by a collaboration called the Standards Oversight Council, or SOC, and I'm Jennifer Thieme, the SOC Program Manager. SOC is an interagency effort to develop high-quality technical standards used across the state. This partnership is over 20 years old, and it was created to ensure uniform standards throughout the state that can be used by federal, state, and local governments. Technical standards, as you may well know as you're tuning in to learn more about them, are science-based technical documents that outline criteria to help ensure conservation practices protect our natural resources. They might be enforceable or not, depending on the situation and how they're referenced in government rules and programs. SOC impacts these technical standards by deciding, with user input, which standards will be created or revised. SOC selects which of our three predefined processes will be followed, depending on the extent of changes we anticipate in the revision. SOC then supports the collaboration among users to create and approve new criteria. Through all of these updates, SOC seeks to ensure quality criteria, to ensure technical standards that can be applied uniformly across the state, and ensure an open and accountable process. Each technical standard that we're going to discuss today followed what we call the full process. With input from the DNR, SOC formed a team of about 10 individuals for each of these standards. Teams were composed of the DNR, DOT, USGS, municipalities, sometimes people from academia, and always private industry. These teams spent about 8 to 10 months identifying the strengths and the weaknesses in the existing criteria. And then they discussed their professional experience in the field, they reviewed the latest research, and then proposed new criteria where they thought it was necessary to improve water quality protection and improve how the standards were implemented. The new proposed criteria was then reviewed by about a dozen experts in the field and revised by the team based on those expert comments. And then each standard was released again, but this time for a 3-week public review, and revised again based on those public comments. Teams wrote responses to each person who commented, explaining why or how each comment was or wasn't addressed. And then finally, at the end of the process, each team submitted the document to the DNR for approval or for final tweaks to make sure it complied with DNR code. And at the end of all these processes, SOC evaluated the team process and then uses that team feedback to improve future processes. In some cases, standards undergo smaller changes that don't necessarily require a whole year or a whole team process. And then we use what we call a modified or a minor process, which only contain the components that are checked in the boxes that you see on this table on your screen. So I encourage you to get involved in this process as well. You can subscribe to our listserv by visiting www.socwisconsin.org. Through that listserv, you'll receive invitations to join teams, comments on draft standards, impact our biennial work plan through our survey, and you'll receive updates about when standards are revised or when there are standard-specific trainings like this one. So thank you for tuning in and enjoy the rest of the webinar.
Today our two presenters are Kim Gonzalez and Jan Kucher, and I'll tell you a little bit about both of our presenters. Kim is the Water Resources Engineer at the Wisconsin DNR. She joined the department in 2014 after working in the National Pollutant Discharge Elimination System regulatory program in California for 5 years, and more recently working as a consulting engineer focusing on Department of Defense environmental compliance and remediation projects. Kim participates in development of technical standards and guidance documents relating to urban runoff and is a statewide contact for utility stormwater permitting. Jan is the Water Resources Engineer at the Wisconsin DNR, and Jan joined the department after over 30 years of consulting, engineering, design, and construction experience. He is responsible for the preparation of technical standards and guidance documents associated with surface water runoff and protection of waters of the state. Jan also reviews customer additive toxicity submittals, for determination of the allowable usage rate for additive projects, and provides civil engineering guidance on project and permit reviews. Okay, as we've mentioned a few times, we're going to be offering professional development hour certificates or PDH certificates after the training. So we'll explain how we're going to do that when we get done with today's webinar. But as I've mentioned, we need you to be logged in with your name. And if there's a department attending and your individual name isn't on there, you can just email me and let me know who's attending. Give me the individual names of the person that wants to receive a PDH. And just a few things on, you have a go-to meeting box, and there's a double arrow up there. You can use that, and then you can minimize your little drop-down box. If you want to leave it up there, that's fine, but it may cover some of the presentation. Also, we're asking that everyone stay muted, and if you're not muted, I will mute you during the presentation just to try to get some feedback when people are on there, so please keep yourself muted. We're going to take questions at the end of both presentations. So at the end, we will be going through the chat line to get all the questions, and we will answer as many as we can today, and if we don't get them all done, we will address those and post those with the webinar when it's posted on the Wisconsin Land and Water website. This webinar is provided today through the Standards Oversight Council, which is SOC, and the State Interagency Training Agency. And I just wanted to mention that about once a month, I publish a sitcom training e-newsletter, and sometimes it's twice a month. And if you're interested in receiving that, I list all the upcoming trainings for the following month. So that is a good opportunity to find out about different training opportunities that we have out there. And I will send out, I'm going to send out a little chat line message soon about the survey, and I also have my email address in that. I think that's about it. Again, please stay on and listen to the entire presentation, and we'll talk about the PDHs at the end. I am now going to turn it over to Kim, and she can take over.
Thank you, Penny. Oh, okay. All right, sorry, we had some audio problems here. Thanks, Penny. The DNR develops and disseminates technical standards to help applicants meet the construction and post-construction performance standards in our rules. During our talk today, Jan and I will provide updates on two recently revised technical standards, those for vegetated swales and for site evaluation for stormwater infiltration. Beginning in 2015, I worked with a team of 10 professionals from both the public and private sector in reviewing and revising the vegetated swale technical standard. The team considered changes that would give users more options and provide clarification. The team's work was published a little over a year ago. And then this fall, the revised site evaluation for stormwater infiltration technical standard was published. And that standard was expanded to include some of the same methodology that the vegetated swale standard had added, specifically regarding infiltration rates in compacted soils. Later this month, DNR plans to publish another version of the vegetated swale technical standard that has been edited to eliminate sections that are now addressed in the recently revised site evaluation standard. The idea is for the site evaluation standard to be like one-stop shopping for infiltration rates. I'm going to give an overview of the revised vegetated swale text standard, and I'll generally follow the same order in which the topics are presented in the standard. I'll point out sections that changed compared to the original 2007 version and spend a little more time on topics for which users have indicated they'd like some additional guidance. Swales are somewhat unique as treatment devices in that they're generally designed to benefit water quality and quantity, as well as to convey runoff. The purpose of swales is to filter and trap pollutants, improve water quality, attenuate peak flow, and in most cases to also promote infiltration. However, swales are not trails, and they are also not parking lots. These activities can cause rutting and compaction, which we want to avoid in our swales. This standard is intended to apply to the design and construction of new vegetated swales, not existing swale systems. So if you are looking for guidance on evaluating your existing swale systems, visit the department website and type in keyword MS4 modeling, or type in the address below. This site includes various guidance documents that are available to MS4s. Some apply exclusively to existing swale systems, while others cover broader topics that may also be relevant. Swales can be an effective option for managing runoff when space is limited, such as along roadsides. They also work well in low to medium density residential areas. Swales should generally not be used in areas where they would have a steep longitudinal slope or highly erodible soils, unless additional precautions are taken to reduce runoff velocity and to protect against erosion. Swales are typically most effective for treating runoff from relatively flat drainage areas of less than 5 acres in size. Swales also work well with other practices such as filter strips, wet ponds, and bioretention areas. When you have a rough idea of how your site will be laid out, but before you get too far into designing your swales, you'll need to determine if vegetated swales are a good match for your project. The primary means of sediment reduction in swales is through infiltration. However, in Wisconsin, infiltration of runoff is prohibited for certain source areas, such as some types of industrial facilities and fueling areas, or in certain locations, such as within a given proximity to supply wells. So it's important to do a thorough evaluation of your site to determine if infiltration and swales are a good match, or if you'll have to explore other treatment options. So let's say you've completed the site evaluation, determined the best areas for infiltration on your site, areas to avoid, and the appropriate infiltration rate to use in your design and modeling. The site plans need to show where the swales will be located in relation to structures, wells, any unusual geologic features, property boundaries, topography, and contributing drainage areas. For design and modeling purposes, it's also important to identify for each swale whether runoff will be entering a swale as concentrated point source or as sheet flow from the sides of the swale, or both. In Wisconsin, the department requires stormwater construction permit applicants to demonstrate that their project will meet the post-construction performance standards in our rules. This is typically accomplished by modeling the treatment system and providing the modeling input and output to the department at the time of permit application. A modeling parameters section was added to the Vegetated Swale standard to clarify meanings of terms sometimes encountered in modeling. One of those terms that we'll spend a little time on is the average swale length to outlet, which is an expression of how far runoff travels on average in a swale. Let's look at an example with a 600-foot-long swale segment receiving runoff as sheet flow along the entire length of the swale. Note that the lengths of culverts are not included in this total swale length. For this example, the average swale length to outlet is simply calculated by taking the total swale length of 600 feet and dividing it by 2, which gives us 300 feet. We take this approach to account for the fact that some of the runoff enters at the top of the swale and has the full swale length available for particles to settle out and for runoff to infiltrate, while some of the runoff enters close to the outlet of the swale without any length of treatment. In the modeling program WinSlam, when you edit the grass swale design parameters, you may need to check the box next to use total swale length instead of swale density for infiltration calculations. Let's see if I can point to it here. In order to allow entry of the total swale length and average swale length to outlet, as highlighted here. Now, if we have a swale segment receiving runoff from a point source, such as from a pond, then the average swale length to outlet is equal to the total swale length. In some cases, it may make sense to combine very similar swale segments for modeling. Let's consider this example where all swale segments, shown in blue, receive runoff as sheet flow from their drainage areas shown in green, red, and purple. Swale segments labeled A, B, E, and F have similar land use, swale geometry, infiltration rate, and flow characteristics, so these swales would be good candidates to group together in modeling. Swale D would not be grouped with the others because, for our example, it has the different land use associated with its drainage area. And although swale segment C may receive runoff from the same land use as segments A, B, E, and F, it isn't a good candidate for grouping with the other segments because it also includes segment D flow from a commercial area and has a higher flow rate and different geometry. Using the equation for average swale length to outlet from the technical standard, we would plug in the swale segment lengths as shown and get an average swale length to outlet of 116 feet for the grouped swales. So the other terms in the modeling parameters section are more straightforward, so we'll move on to the next section, velocity and depth criteria. The maximum velocity and depth values did not change from the previous version of the standard. You should still design to keep the 2-year 24-hour peak flow velocity at 1.5 feet per second or less, and water depth at or under 12 inches. If you're having trouble meeting the velocity and depth criteria, you can include permanent ditch checks, but keep in mind that swale areas immediately upstream of ditch checks may need additional maintenance. The system should be designed to drain within 24 hours after rainfall. However, we did add an exception. It is okay if the system takes longer than 24 hours to drain as long as wet-tolerant vegetation is planted, and the system drains within a maximum of 48 hours. Regarding swale geometry, the team did make some changes. Swale side slopes should be no steeper than 3 horizontal to 1 vertical, except for roadway swales, where side slopes as steep as 2.5 to 1 are allowed. If possible, design swales with flatter side slopes to reduce erosion and to increase infiltration. We increased the maximum allowable bottom width of trapezoidal swales from 6 feet to 8 feet, primarily to facilitate swale construction. The reason why we limit the bottom width at all is because channelization can occur, in which case we have a situation where modeling demonstrated the system would meet the performance standards, but in reality, after channelization, the system is undersized for adequate treatment. So if your project really needs more than 8 feet of swale width, consider lengthwise dividers so that the bottom width of any given cell is no more than 8 feet. Another change is in allowing flatter longitudinal slopes. Although flatter slopes slow runoff down, that's the runoff that's traveling through the swale, and thereby improve infiltration, the trade-off is that ponding is more likely to occur and to kill off swale vegetation. The minimum longitudinal slope allowed has been decreased to 0.5%, and the maximum is still 4%. However, the standard does specify that swale segments with longitudinal slopes less than 1% and an infiltration rate less than 0.13 inches per hour must be planted with wet-tolerant vegetation. The primary reason swales are so effective for managing runoff is due to the vegetation. Vegetation on the surface prevents erosion during rain events, and the root system simultaneously holds soil together to keep it in place and open it up to improve infiltration. For these reasons, you should carefully consider how to successfully establish vegetation in your swales, how to prevent vegetation from dying off once established, and to manage problem areas. Swales should be planted with native vegetation if possible, or turf grass. Depending on expected runoff and swale characteristics, use vegetation that is salt-tolerant or wet-tolerant, or both. The construction section of the standard is new and has detailed information about how to best protect your swales from compaction and clogging during construction. It also has guidance for restoring swales that have been compromised. Previously, compaction mitigation was always required. While it's still important to decompact soils for the best swale performance, we recognize that for some projects, swale decompaction will not occur. For those situations, we developed an approach to account for compaction by reducing the infiltration rates used in modeling. However, since that methodology has been incorporated into the site evaluation standard, DNR plans to remove it from the swale standard, and I'll let Jan touch on that topic during his presentation. The pretreatment section is another part of the standard that the team expanded. Wisconsin rules require pretreatment of runoff from certain source areas prior to infiltration. We'll look at the pretreatment options included in the standard. Vegetated filter strips are a convenient choice for pretreatment of sheet flow runoff into swales because they're basically just the side slopes of swales. Anything more than 5 feet of filter strip length in the direction of sheet flow can be counted toward pretreatment. Ideally, we'd like to see 10 feet. However, filter strips are not sufficient pretreatment for runoff flowing across more than 100 feet of impervious or non-vegetated areas. When runoff is entering as a point source, a segment of vegetated swale can be used as a pretreatment area. Using Stokes' law, a 1-foot flow depth and 1.5 foot per second velocity, we calculated that 100 micron sized particles, basically sand, would need about 80 feet of swale length to settle out. These pretreatment swale areas are where sand particles will accumulate, and we can expect reduced infiltration capacity, spotty vegetation, and a need for periodic sediment removal in these areas. The department considers an 80-foot pretreatment swale segment sufficient to serve a drainage area of 5 acres or less. And we have wet ponds or other sedimentation devices which can accept runoff entering as a point source or as sheet flow, or both, depending on the site and the type of device. Additionally, your site may need other pretreatment devices such as oil water separators, depending on the source area. So next is the infiltration section. You may be wondering about a term that pops up throughout the standard, the effective infiltration area. Probably the only situation where you would have to calculate the effective infiltration area is when modeling indicates a design will meet both the TSS and peak flow performance standards, but cannot meet the infiltration performance standard. In that case, add up all the effective infiltration areas as described in the standard and show that they exceed the minimum area required in our rules for infiltration. However, if your design is on target for meeting the TSS, peak flow, and infiltration performance standards, then you can completely skip calculating the effective infiltration area. So at some point in your design process, you will have completed the site evaluation for infiltration and followed the steps in that standard to obtain an infiltration rate appropriate for your soils. That infiltration rate assumes infiltration under static conditions, such as in a pond. However, to account for the fact that infiltration in swales occurs as water is flowing instead of ponding, the static infiltration rate is divided by 2 before being used for swale modeling. Some of the models refer to that as the dynamic infiltration rate or design infiltration rate. While we realize this is a conservative approach, it's better than the alternative of an undersized system that may result in flooding issues, safety concerns, and insufficiently treated runoff. Last but not least, be sure to check out the considerations and operations and maintenance sections. Those sections of the standard will come in handy to address unusual challenges that may arise during design or implementation of the practice, or when you're trying to figure out what to include about swales in the long-term maintenance agreement. So that's all I have for you today. I will now hand it over to Jan for his overview of the site evaluation for stormwater infiltration standard.
Thank you, Kim. And this is Jan Kucher. I'm going to be telling you a little bit about our new updated technical standard, 1002, site evaluation for stormwater infiltration. And we worked on this over about a year, actually. So what I'll do here is tell you a little bit about that and how important water is. Here's a shot of Tucson looking at Kip Peak. And although I certainly appreciate the desert, I appreciate our waters here as well. And when we say one of our goals here, the main goal is to protect water resources of Wisconsin, or also called waters of the state. And so when we look at where our technical standards are on the website, I'm sure many of you are familiar with with this. It's on dnr.wi.gov, topics, stormwater, and standards. Post-construction, we also have the construction. But the circled standard down here is the location of a PDF of our 1002 evaluation for infiltration. To show you this figure that we created for our technical standard to try to avoid some confusion. If you're like me, you were confused by sometimes it's called, someone will say, it's at the top of infiltration, it's the bottom of infiltration, and we came up with the term native soil interface. If you see where the cursor is here, that's the bottom of infiltration device, a location where infiltration tests would be performed. Now this alleviates some of the concern. I'll be using this, referring to this as we go forward. The other item here is the soil evaluation depth, which the critical depth is 5 feet below the native soil interface here. And it's in that depth below the native soil that we look for groundwater, seasonal high groundwater, or bedrock. Okay, so in the technical standard, we laid out 4 steps, A through D, regarding how to evaluate soils for infiltration. And A is initial site screening here. And as you can see, we move to more detail and more field work as we move forward. And bold on the bottom, as Kim had mentioned, is the obviously when water's moving, it's considered dynamic, and it has half the infiltration of static, or what we typically calculate here in our 1002 standard. So I'm going to move through each one of these steps, give you a short yet tedious discussion. So with step A, initial site screening, it's essentially a paper study. Common sense, in the office, gather information on a site, and hopefully, in an ideal situation, start out with a good conceptual site plan. I don't know if that makes sense, good and conceptual at the same time, but it's conceptual so you have an idea of where the drainage is going to go and potential areas to investigate. And look at wetlands, waterways, wells, topography, the full list of information typically due with our notice of intent applications for permit coverage. Karst is important as well, obviously. Channelization through bedrock directly to groundwater is not nice. So step B, we get a little bit more detailed here and do a preliminary field investigation of the initial site screening. In this case, soil borings are acceptable. Take a look at a potential site, potential area of the proposed facility, and to look at the soil texture, and also potentially look at exemptions. Obviously, coarse sand does not work as a marvelous infiltration media. I suppose if you hit hard clay, also give you additional considerations to look at. Okay, then we move into step C, where the rubber hits the road, really, with looking at the actual infiltration rate at the native soil interface, as I mentioned before, in Figure 2 in the technical standard. So we've got the 3 steps here, and as you can see, field evaluation, specific areas, potential infill rate exemption, which is 0.6 inches per hour from an actual measured condition, and then the infiltrate rate determination, options 1 through 3, which are a bit more detailed, more straightforward. So for example, in step C1, field evaluation specific infiltration areas, this is, you can take a look at figure 2 for the test pit location from the native soil interface. Also to look at the morphological soil profile. And the beauty of a test pit is that you can look for bedrock, groundwater, seasonal high groundwater, potential modeling of the soil. Now here's table 1, which summarizes a different type of BMT, for example, on the left column, and the test pits, and the number of test pits given the type of trench or basin. Again, just a reminder, the native soil interface and the 5 feet below the native soil for the evaluation depth. So step C2 is infiltrate rate exemption, in which after doing a test pit, be able to take a look at, do an actual measured infiltration rate to determine if the infiltration rate is at or below 0.6 inches per hour. This is outlined in NR 151 as well. And a perfect condition to look at representative areas. So step C3 is an infiltration rate measurement. This is where we get into the 3 options, which are a bit more prescriptive and detailed. And I'll walk you through these. Infiltration option 1 is what infiltration is not measured, and compaction is just a minute here. Soil compaction is mitigated. Option 2, infiltration measured with in-field device such as a double ring infiltrometer, and soil compaction is mitigated. Option 3, infiltration rate not measured and soil compaction is not mitigated. And a side note here is, as you go down with more unknowns, the factors of safety increase. So probably an ideal situation is option 1, option 2, infiltration rate is measured and the soil compaction is mitigated. Now, I should back up a second and remind you of mitigation, because in this case we talk about the mitigation as deep tilling or deep ripping, or reducing the density of the soil to promote infiltration. Another ideal mitigation is to plant deep-rooted vegetation that will pry open the soil and provide some wicking for surface waters. And one thing to consider additionally is that the ideal condition is to avoid construction compaction at the beginning, or stockpiling materials on the site, which will add to compaction. No, this isn't always ideal, but possibly consider fencing off the area once the infiltration area is identified. So I'm going to drop down here to option 1, in which the infiltration rate is the lowest infiltration rate from table 2 within 5 feet of the native soil interface, as in figure 2. So take a look at an example. If the lowest infiltration rate is 0.3 inches per hour, which is silt loam, at a location 2 feet below the native soil interface. Now this 2 foot down the native soil interface, the proposed native soil interface may be some footage below existing grade, just to keep that in mind. Then using table 2 here for silt loam, I'm going to look for silt loam here, and it's 0.13 inches per hour. And this is table 2 for static in the technical standard. So that would be our design infiltration rate, that 0.13 inches per hour. Okay, then I'm going to stop down to infiltration option 2, in which the infiltration rate is measured with an infield device and the soil compaction. I'm sorry, without an infield device and the soil compaction is mitigated. I think I read that wrong. Infiltration rate is measured with infield device. So we have two 2-hour double ring infiltration tests at 5 water depths. And then we calculate the geometric mean from this information and determine the textural infiltration rate, Tn, at the native soil interface. There's a typical double ring infiltrometer. Modified Philip Dunn could also be used. Here's another double ring in progress. And the standard allows a 2-hour double ring infiltration test versus the ASTM 24 hours. It's a lot more expedient and reduces the water usage. So here in option 2, infiltration option 2, determine the lowest textural infiltration rate within 5 feet below the native soil interface. That would be from table 2. And divide the lowest infiltration rate by the T sub L, which is the lowest infiltration rate, to get a ratio R. This is used to determine the correction factor from table 3. Then the infiltration rate is the geometric mean, G, divided by the correction factor. So here's an example. Say we've got a geometric mean of 1.45. And just a reminder, the geometric mean is defined in our definitions of the technical standard. So the textural infiltration rate is 0.24, being loam from table 2. And the lowest infiltration rate within that magic 5 foot below the native soil interface is 0.5, which is sandy loam from table 2. So the ratio with the division of those two is 2.08. And using table 3, the correction factor would be 2.08. The ratio, 2.08, and the correction factor would be 3.5, sorry. So the actual design infiltration rate is the geometric mean divided by the correction factor of 3.5 for 0.41 inches per hour. And here's the table 3 where the 3.5 came from, with the ratio falling into this range. So the last option is option 3, where the infiltration rate is not measured and soil compaction is not mitigated. Now this is probably the worst of all 3 in terms of unknowns, and thereby the need for a higher factor safety rather. So with this situation, we multiply the textural infiltration rate, TL, from table 2 within the magic 5 foot of the native soil interface by the correction factor from table 4. And in the example here, if we had sandy loam of 0.5 from table 2, and the correction factor, sandy, is 0.4, by multiplication we come up with a 0.2 inches per hour for the design infiltration rate. a reminder of using Table 2 again, and Table 4 for the correction factor. So once we've done our information gathering in the office and paper study and field work with hopefully actual measurement of infiltration, it's compiled in a brief and concise report, hopefully concise, with map and key information, the soils information, and the proposed infiltration surface, the rate for design, and to be submitted with the construction plan submittal for permit coverage. One thing I neglected to mention early on would be the tremendous advantage of getting a proposed topography with the conceptual drawings, as well as ground shots, existing conditions at the proposed basin, and elevation shots of the proposed native soil interface and bottom of the test pits. These are all very helpful. Then we go on to qualifications we mentioned in the technical standard. And we've got the steps A and B, which are the preliminary, can be performed by a licensed professional with experience in soil investigations, interpretation, and classification, acceptable to the local authority. Now, step C, we took a bit of a change here because of the difficulties with many sites across the state with infiltration in design. So we looked at 5 years out, and I mean the first 5 years looking at licensed professional soil scientists and professional geologists or other licensed professional with 5 years experience acceptable to the authority until December 31, 2022. Now, after December 31, 2022, Step C would be performed by a professional soil scientist or professional geologist. So in summary, for the site evaluation for stormwater infiltration, it's important to perform preliminary info gathering, as I mentioned, probably starting with the paper study, and then getting a bit more detailed as the information is gathered. Gather soils and perform test pits with good visual interpretation of the soil and potential for modeling, bedrock, groundwater, seasonal highs. Prepare the soil profile information, and we have a form in the back of our technical standard which can be used to document those test pits. And then estimate the infiltration rate for design. As I mentioned, the more field work, the better. More unknowns if you're not mitigating and not actually measuring the infiltration rate. And then prepare a clean, concise, to-the-point evaluation report. The DNR has references on our website, the post-construction technical standards and the construction and stormwater guidance that's existing and proposed here. And I'm sure Kim and I would both welcome calls to assist as necessary. Happy to do that. And thank you for attending. I think we've got around 100 people on the call. I appreciate your attendance, and all questions are good. Kim and I will be happy to see if we can help you out on those. So Penny, do you want to take over here?
Hey, so we do have a few questions that have been coming in to us, and we'll be addressing those. And there was just a few more that came in. So again, we're taking questions by the chat line. So if you can send me a message, and then we're going to review those and see how we can answer those to the best of our ability. So keep on sending in your questions, and we're going to be on here until at least 11 o'clock. We hope to finish up by then. So send in your questions to us, and we'll be addressing those shortly.
And is 1005 still in draft format. The 1005 standard was finalized in September 2016, and that is the current version. What I mentioned during my talk was that we are in the process of eliminating sections from the swale standard that are now covered in the site evaluation for stormwater standard, specifically having to do with compacted soils. So those changes are in progress, and since they're considered minor, there's no change in how this situation is handled. It's simply being moved from one standard to another. There will be no draft published. It will just be updated as soon as we're ready to do that. It looks like there was another question. What does soil compaction mitigated mean? I can say for the vegetated swale technical standard, the team did identify a couple different approaches to mitigate swales that are under construction for compacted soils, but those pertain specifically to swales, and that's located on page 5 in the construction section of the standard. Now, the site evaluation standard is designed to apply to all infiltration devices, and there's a definition of compaction mitigation, I believe, in the definition section of the standard, but that's a more general definition. You should definitely check your, if you're designing a swale, see if there's any specific guidance for compaction mitigation in that standard, or if you're designing a basin or something, check those specific standards to see what approach is recommended to mitigate for compacted soils. I also see that there's a question regarding quantifying peak flow control in swales, and I think I'm going to take that one and talk to some of my colleagues in the program and publish a response to that with respect to the best way to model and quantify peak flow in swales. So I'll be following up with that. Please check back on the Wisconsin Land and Water website for a response to that question. Go ahead, Jan, if you have another question.
Hi, this is Jan. There was a question on what if 2 hours is not long enough for the double ring to completely drain? I guess I would take a look at the soils closer, possibly another test pit. Maybe move over a little bit to see if that was just an anomaly. There was something there that stopped it to drain. But it should, if the investigation went below the native soil interface and looked at the soil texture, it would give us a good idea of what infiltration rate it would have. I guess that's the only thing I could think of at the moment, is to just do a little bit more soil investigation. There was also a question about why did we remove licensed professional engineer from the standards. And this was a topic of a lot of discussion in our year-long technical standard update. It was decided that the protection of the surface and groundwater is extremely important, and in order to promote the best design of infiltration basins, it was noted that the infiltration rate is not, if it's not accurately estimated, the basin can fail. And this has been a challenging standard to update. We created a work team with 11 technical reviewers, 6 engineers, a soil scientist, and a DSP representative. And the goal is to protect waters of the state, groundwater and surface waters. And we reviewed it over a 13-month period, and after the draft was then reviewed, by 12 technical reviewers, then went to a 21-day review. And note that the technical standards are not code and only become code when a governmental body adopts them as law. And they're meant to be advisory guides for design and construction. The DNR cannot make law. This is only handled by the legislature. So, all things considered, it became the best recommendation is to go with the soil scientist and the professional geologist. This wouldn't kick in until December 31, 2022. So there's time to look at this as we go forward and discuss the pros and cons of this. And I appreciate the question. There's another question. If the native soil interface is 5 feet below the bottom of the bioretention soils, should the fill just be designed with fine sand? That is a good question. I think that we'd have to look at the technical standard as well as NR 151 to look at the potential filtration capabilities of the particular grain size you're looking at with fine sand. Initially, it looks like it might be a good option, but I think a finer grain material would potentially work better and would need to be looked at.
I see that somebody had a question about the effective dates of the 2 technical standards. The Vegetated Swale technical standard was finalized, like I said earlier, September 2016, and the site evaluation for stormwater infiltration was finalized in September 2017, so just a couple months ago. Somebody suggested that the DNR develop flowcharts for kind of clarifying how to do all the steps in the site evaluation standard. Thank you for that suggestion. It's something we'll keep in mind when the standard is next up for revision. Let's see. Oh, there was a question. Can Kim describe the difference between pretreatment swales and regular swales? So the pretreatment swales, like I mentioned during my talk, those are areas that you should definitely keep an eye on. They may need some additional maintenance compared to other areas in your swale system, in that that's the location where the larger particles are more likely to settle out. As far as you could still model that area in your models, one thing to keep in mind with the pretreatment areas is that those areas are not counted toward the effective infiltration areas. So if you are just trying to go for meeting the minimum infiltration area and you cannot meet the infiltration performance standard, then keep in mind that pretreatment areas do not count toward the calculation of the total effective infiltration area on your site.
Kim, there's a question. This is Jan. A question that would a licensed geotechnical engineer civil degree be acceptable? This would be perfectly acceptable. Our recommendations are for 5 years out, and then after that being a licensed soil scientist or geologist. And as I mentioned, that this is this is up for public comment as we go forward, and we change these standards as necessary. So I hope that answers your question. There's a question about groundwater mounding calculations, and that's good potential for seasonal groundwater mounding. We discussed that. At the moment, I can't recall where we talked about that in the technical standard. As I recall, it was something that needed to be modeled as part of the DSPS process of air permitting when a pipe is used on a project external to a building. Just what I'd like to do is get back to you on that one. There was a question regarding SOC standards. SOC standards commonly referenced in the local ordinance, so the PSS requirement would be law. That may well be the case in certain circumstances. Are there other questions? I don't see any other questions. Penny, I've got... okay, I've got a question here. Are soil borings no longer acceptable soil textural evaluation method when determining the design of filtration? We recommended soil borings for step A and B, and soil borings acceptable for step C if the native soil interface is below 15 feet. So we don't need to have a test pit deeper than 15 feet. And also sidebars, we don't expect people to be going into trenches that aren't safe. They need to be following OSHA requirements. The beauty of the test pits is you can see the soil stratification, soil profile. So 1056, are there any other questions? Figure shown in the site assessment discussion appears to show the depth of the soil test being shown as a function of depth from the ground surface instead of from the bottom of the swale. Yeah, that's a correct comment. The intent is to show that the depth of the test pit goes 5 feet below the native soil interface. And we could have showed that a little bit better, a little bit clearer.
Okay, I think that does it for questions. Like I said, Jan and I will be following up on any questions we did not answer for you today. And now I'll hand it over to Penny, and she'll give some final announcements. Thank you.
Okay, I just wanted to mention how we're going to do the PDHs. I sent out a chat line before that had my email address, and it's also on the screen that just came up. So what we're asking is, if you do want a PDH certificate sent to you, to email me. I took down all the people that were in attendance today, and that's how we're going to base off who's eligible to get them. We're only allowing them for people that attended today's live session. We did max out, so there's quite a few people that weren't able to join us, so congratulations on getting on early and getting in. If there's any more questions, others we're going to wrap up here pretty quickly. I see people already signing off. So again, I thank Jan and Kim for a great presentation, and for SOC for working on this for us. It will be posted on our website within a couple of weeks, and if you have any questions, please email me or Kim and Jan, and the questions that weren't addressed today, again, will be posted with the webinar on our website. So I think we have them all. This is the last call. Otherwise, we're going to be shutting down. Last call for questions. Okay, thanks everyone. Have a great day.